Hi and Assalamualaikum everyone. My name is Fatih Nabila binti Hassan. Today, our group will be presenting on Green's theorem, one of the important theorems in vector calculus. Before we move on to the case studies, let me briefly introduce what Green's theorem is. Green theorem is a two-dimensional version of the fundamental theorem of calculus for vector fields. It was first introduced by the English mathematician George Green in 1828. Later, it was independently discovered by Mikhail Ostrogensky, and George Green's works gained recognition after it was promoted by Lord Kelvin in 1846. Today, Green's theorem serves as the foundation for several important concepts in vector calculus, including Stokes' theorem. Now, let's look at where Green's theorem can be applied. First, it is used for a vector field in a two-dimensional plane over a region, usually denoted as D. Second, the boundary of the region, called C, must be simple, closed, and piecewise smooth curve, and it should be oriented in the counterclockwise direction. Lastly, the vector field components must have continuous partial derivative throughout the region. However, there are also situations where Green's theorem cannot be applied. For example, it does not work for open curve or self-intersection curve. The region D must also be simply connected, meaning it should not contain any holes unless a generalized version of the theorem is used. In addition, Green's theorem is limited to two-dimensional problem. For three-dimensional vector fields, we use Stokes' theorem instead. That concludes the introduction to Green's theorem. Now, I would like to hand over the presentation to my group members who will explain the first case study. Thank you.
Assalamualaikum and good day everyone. My name is Nur Erna Farisha binti Ahmad Zamri, and today I will present case study 1, which demonstrates the application of Green's theorem in evaluating a line integral. So now the first one is the problem asks us to evaluate the coastline integral. So the equation is 2x squared y plus y cubed dx plus x squared plus 2x cubed y dy, where C is the boundary of a triangle with vertices at 0, 0, 3, 0 and 0, 2 oriented in the counterclockwise direction. Instead of calculating the line integral directly along each side of the triangle, we apply Green's theorem, which converts the line integral into a double integral over the enclosed region. This simplifies the calculation and reduces the amount of work required. So the first step is to identify the function px squared equals to 2x squared y plus y cubed, and for qxy is x squared plus 2x cubed y. Next, we compute the required partial derivative. The partial derivative of q respect to x is 2x plus cx squared y, while the partial derivative of p with respect to y is 2x squared plus 3y squared. Using Green's theorem, we subtract this derivative to obtain the integral, which is the equation is 2x squared 3y minus 1 plus 2x minus 3y squared. The region of integration is the triangular area bounded by the given vertices. Therefore, the limits of integration are y from 0 to 2 and x from 0 to negative 3y over 2 plus 3. After setting the line integral with this limit, we evaluate it and obtain the final answer of 9 over 5. To verify the manual solution, we also use Maple software. The Maple commands calculated the same partial derivative, generated the same double integral, and produced the identical final result of 9 over 5, confirming that our manual calculation is correct. So, in this case study 1, it demonstrates how Green's theorem provides a more efficient method for evaluating line integrals by transforming them into double integrals over a region. So, the agreement between the manual calculation and the Maple solution confirms the accuracy of our result.
Now, I will present case study 2. In this case study, we are asked to evaluate the line integral given using Green's theorem. The curve is a unit circle, x power of 2 plus y power of 2 equal to 1, and it is oriented in the counterclockwise direction. The first step is to identify the function p and q from the given equation. For pxy, we got 2y plus e power of x, while qxy equal to 4x plus cos y. Next, we need to compute the required partial derivative. For derivative of p with respect to y, we got 2, and the derivative of q respected to x, we got 4. So according to Green's theorem, we subtract these two partial derivatives. Therefore, 4 minus 2 equals to 2. This means the line integral is converted into a double integral over the region enclosed by the circle. Since the region is a circle, so it is much easier for us to use polar coordinates. The limit of the integration are from 0 to 1 for r, because it is a unit circle, and from 0 to 2 pi for the theta, representing one complete revolution around the circle. After we evaluate the double integral, we will obtain the result of 2 pi. So, to verify the solution of the manual calculation, we are going to use Maple software. First, we start by set up the Maple, restart, and load the vector calculus package so that we can access the function needed to solve the equation. Next, we will define the function pxy and qxy that we obtained before from the line integral. And after we key in the input, we will get an output that say function pxy is 2y plus exponent power of x, and function qxy is 4x plus cos y. Next, step 3, we will calculate the partial derivative of q with respect to x, and we will get 4. We will do the same to partial derivative of p with respect to y, and we will get 2. After we compute the partial derivative, we will move to step 5, calculate integrand for Green's theorem, which is dq over dx minus dp over dy. From the output, we will get the integrand for the double integral, which is 2. For step 6, we are going to convert the integral to polar coordinate for the circular region, and then we will try to find the limits for both r and theta using the given formula as shown. From there, we will obtain the limit for r is 0 to 1, while the limit for theta is 0 to 2 pi. We move to step 7, which is evaluate the inner integral first with respect to r. Then we will obtain the output that show inner integral result equal to 1. Then we move to step 8, which is evaluate the outer integral with respect to theta. And we'll finally obtain the final result, which is 2 pi. From here, we verify that the Maple solution is same to the manual calculation. That's all from us for this presentation. Thank you.